Now let's take a look at motor vehicle crashes. We're going to be focusing on three equations here. The kinetic energy equation, which I just erased. There we go. And a force equation and an acceleration equation. So let's go take a look. All right, so in motor vehicle crashes, if we look at the kinetic energy, again, it's 1/2 mv squared, where in this case, m is your mass and v is the velocity you were traveling when you impacted another car, a tree, a bridge abutment, something along those lines. And just as in gunshot wounds, because velocity is squared, the kinetic energy from crashing at 20 miles per hour is not going to be twice that as if you crashed at 10 miles per hour. It's going to be 4 times because we're squaring it. So speed is really the significant factor in trauma with motor vehicle crashes. It's not so much your mass, it's mostly your speed or your velocity. So let's take a look at the forces involved. Okay, so the forces exerted on you at impact, you can calculate that by F equals ma. F is force measured in newtons, m is your mass in kilograms, and a is acceleration in meters per second squared. Now acceleration in this case is not gravity. Acceleration is how quickly are you slowing down or speeding up. In this case, when you crash, it's going to be slowing down because your final velocity, your final speed is going to be 0. So here we have here. By definition, acceleration is change in velocity over change in time, which is basically what is your speed change and how long did it take for that speed change to occur. That's your delta t, your change in time. So if we substitute change in velocity over change in time in for acceleration in this equation here, we end up with this. Force equals mass times acceleration, which is equal to mass times delta v over delta t. So we rearrange, and this is what you get. Force times change in time is equal to mass times change in velocity. I put a box around mass and velocity because you cannot change these facts. Your mass is your mass, and your velocity is velocity. If you were traveling 40 miles an hour when you hit the tree, you were traveling 40 miles an hour when you hit the tree. That means that force is indirectly proportional to time. This is crucial because if we can increase the amount of time it takes to impact, it then makes the force smaller. So that's the goal of airbags, which are called supplemental restraint systems, or SRS. What happens is when you hit the airbag, when the airbag deploys, and you hit the airbag, let's say you're not wearing your seatbelt, you hit the airbag, it's going to slow you down. You're not going to hit the steering wheel instantaneously. It's going to slow you down. It might seem it's a fraction of a second, which it is, but anything you can do to drive up your delta t drops the force exerted on you, okay? They are inversely proportional. So the goal is to increase the time of impact. And that's what stunt people do. When they jump out of a moving car, they don't lay still, they roll. Or when they jump out of a window, you don't see it, but 3 stories below, they jump into an airbag. And what the airbag does is it increases the amount of time it takes to come to a complete stop. They increase your delta t, which decreases the force. It's the same principle as falling off of a step ladder onto a thick carpet versus falling off of the same step ladder onto concrete. The thick carpet will cushion your fall. It's increasing your delta t, so it's lowering the force involved in the incident.